Okay, so welcome everybody to the last day of Beyond ID 9. In the following 1.5 hours, we have two talks. The first one is the invited talk by Varun Jog. He's affiliated with the Department of Pure Mathematics and Mathematical Statistics at the University of Cambridge. His research includes information theory, learning theory, and convex geometry. Today, he will talk about estimating location parameters in sample-heterogeneous distributions. Varun, the floor is yours, please.
Yeah, thank you for the nice introduction. Thank you also to the organizers for inviting me, and I'm sure it's very hard to find a time that to kind of organize a conference that is going across various time zones. So kudos to the organizers for figuring out a proper time that works. Um, right. So my talk today is about estimating location parameters in sample heterogeneous distributions. The title is a bit obtuse, like it doesn't make it clear what I'm going to talk about. But since the title of this workshop is Beyond i.i.d, I thought this work that I did with a student of mine, Ankit Pensia at UW-Madison, and my colleague Pauline seemed like an appropriate fit. Okay, so what's the problem that we are trying to solve? The motivation comes from noisy peer review. So in peer review, what we typically have is you have a bunch of researchers who write a paper, they submit a manuscript. The manuscript has some rating. So typically, when you submit to a conference, you're asked to rate a paper on a scale of 5 or something. So the manuscript had some true rating mu, which is of course unknown. But to find it out, the manuscript is now sent out to reviewers. The reviewers are all unbiased, but of different quality. So, for instance, reviewer 2 might actually know, might guess the correct rating mu, but there might be some variance around reviewer one's actual score. Reviewer 2 might have absolutely no idea what's going on. So their variance is basically infinite. They don't know where the actual mu is. They don't know. They're not familiar with the topic and so on, and so on. You can have various reviewers with different level of expertise. So basically, you can think of variance as expertise. um, and as a conference organizer, what you receive are these 5 reviews, and your job is to figure out what is the true rating of this paper. The difficulty here is that these 5 reviewers, even though they are unbiased, which means that they are giving you a score which is centered around the true mean mu, you don't know who is a good reviewer, who is a bad reviewer. So all the variances can be different, and not only can the variances be different, you have no idea what the variances are. So that makes it quite challenging to gather all these scores and eventually figure out what the true rating of the paper is. Another related situation where a similar problem shows up is in crowdsourcing. So similar to reviewing, you can have, let's say you're crowdsourcing for a single item, and you have an item, let's say headphones on Amazon that someone is trying to buy, and each reviewer has some rating. But again, there are these variance parameters which indicate the expertise of the reviewer. And again, the reviewers might have different variances. Your job when you're trying to buy the item or give the item a proper rating is to combine all these 4 reviewers ratings into the actual rating mu. So you are trying to figure out what the true rating is. But again, the difficulty is you don't know, you don't are rating all the items. But if you look at any particular item, um, the mean, for example, if you look at item number 2 and look at the row corresponding to item number 2, the mean is mu2 everywhere, but the variances differ depending on the user. And if you look at a column, then the mean is changing because mu1, mu2, mu3 are different items, but the variance of the reviewers remains the same, which means that if you're a good reviewer, then your variance for a headphone is basically the same for your variance for a laptop. So you're considered an expert, equal expert in all these three item categories. So mathematically, what this means is that you have this array of random variables, and if you're looking at the jth item and the ith reviewer, so xij is the rating for the jth item by the ith reviewer, then this is some Gaussian random variable with mean mu j and variance sigma I square. So mu j is the rating of the item, the true rating, and sigma I square tells you what is the expertise of the reviewer who rated that item. Okay, so based again, the problem is the same. If you now think of this as the entire ratings to all items as a vector, then that vector is distributed as normal with mean mu and a covariance matrix, which is sigma I square times identity. And your goal is the same, that you have these column vectors and you need to estimate the vector mu based on these samples. So again, essentially exactly the same setting. You have entangled distributions that they have the same mean but different variances. Difficulty is you don't know the variances, and the variances are not the same. Right. So the setting that we'll be considering in this talk is basically is the following, that in our mind we are always going to assume that or the way we are going to think of the problems is that you have n reviewers who are reviewing these items, but some k of these reviewers are actually good reviewers in the sense that they have small variance, and the remaining n minus k might be really bad reviewers in the sense that they can have as large a variance as you want, like almost infinite variance. Um, and even if even though there are only k good reviewers and n minus k bad reviewers, we want to be able to give an estimate of mu. So just by sort of identifying who is a good reviewer and then only using their ratings intuitively to figure out mu. And what will happen in the stock is that k can be as small as log n. So you might have a million different reviewers, but only about 10 of them need to be good reviewers for you to have a good estimate of what the true mean is, right? So that's kind of the picture that one should have in mind, that k good reviewers and everyone else is bad. So roughly log n good reviewers and n minus log n very bad reviewers. Okay. Okay, so here's a warm up. So initially, let's say the first thing that one might do when you're trying to estimate the mean is to use the maximum likelihood estimator. And we can explicitly calculate the maximum likelihood estimator in the setting where xi are Gaussian random variables. So which is kind of what I've been describing so far. Of course, the maximum likelihood estimator requires you to know what the variances are and which sample corresponds to what variance. But let's say you know that. Then this is kind of like a simple homework exercise that you can actually, in closed form, figure out what the maximum likelihood estimator is, and it looks as shown on the slide. And in particular, the distribution of mu hat, which is the MLE, turns out to be centered around the correct mean mu, but it has variance which is given by 1 over summation of 1 over sigma I square. So of course, if all the sigma i's are same, then this is equivalent to the sample mean. And we know that at least when everything is Gaussian, the sample mean or this maximum likelihood estimator is going to be information theoretically optimal when you think of L2 error. But even in this setting, you can see that this estimate need not be consistent. Like the consistency of the estimate will depend on how the variances are behaving. So for instance, if the variances are if sigma I is equal to I, the standard deviation is I, then this denominator 1 over summation, so that summation part is going to be something bounded, because 1 over 1 square plus 1 over 2 square plus dot 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 is going to be something bounded, which means your mu hat is centered around the true mean with some constant variance. And that means that the variance is not going to 0, which means even though you're getting infinite samples, there is still some constant uncertainty in where the actual mean lies. Okay, so it need not be consistency, again, it depends on the quality and quantity, not just on the quantity. Okay. So what are some natural ideas that we might use? So I said that the previous slide assumed that you know what the sigma i's are. So you are getting samples that are independent, non-identically distributed, and sigma is unknown. But what if you don't know the sigma is? Well, one thing that you could do, you could always just take the sample mean. So you have these x1, x2, xn. There's nothing stopping you from just taking the x1 plus x2 plus xn divided by n. If you do that, then your estimate mu hat is now distributed as, it is centered around the correct mean, so it is an unbiased estimate, but its variance is given by summation of sigma I square over n square. And this is optimal if your samples are i.i.d. So if all the sigmas are same, then this is optimal. But you can see that this estimate is very sensitive. So even if one of the xi's has a very large sigma, so just imagine that one of the sigmas is basically infinite. Um, in that case, the distribution of mu hat happens to have infinite variance, which means that if you want mu hat to have some bounded variance, like you want to make sure it's well behaved, then every single point needs to be well behaved. So as I said, k is the number of good points in our mind. So for the sample mean to work well, all the points need to be good. You cannot have any really badly behaved reviewers. Any one badly behaved reviewer can break the system. Um, and even for i.i.d. distributions, you do need to have bounded moments. So for Gaussians, of course, we know the moment sigma square, but if you don't have Gaussians, you need the bounded moments assumption. Now, you might know that maybe sample mean is very sensitive, like even 1 point can break it. So a more robust version of that might be the median. So median is typically more robust than the sample mean, and that does turn out to be the case here. So in particular, one can show that if you're looking at the median instead of the mean, then the median depends on roughly square root n of the good points. So as long as you have square root n good points, so that's still like a vanishing fraction of good points. So n minus square root n really bad high variance points, and only square root n good points, you can show that the median performs well in that setting. And and the error in this case is as large as sigma sub root n. So what this notation means is that you have sigma 1, sigma 2, sigma n, which are these unknown variances. You arrange them in increasing order. So the best point, so the reviewer with the best lowest possible sigma and sigma sub bracket 1 and so on. So sigma sub root n is the quality of the square root nth reviewer. So that is the square root nth smallest variance. And the error for the median is controlled by that quantity. So if square root n reviewers have small variance, then the median is assured to perform well. And just to give an idea of how the proof works for the sample median, the problem here can be reduced to estimating the bias of a coin. So basically, you want to make sure that the median lies between mu plus epsilon to mu minus epsilon for some epsilon, and so you need to figure out how much probability difference should be there. So when you're exactly at mu, the coin is fair, so it's half and half. When you go slightly beyond mu, the coin becomes biased. So how far beyond mu do you have to go so that the bias of the coin can be detected in n samples? So this problem, this is standard kind of hypothesis testing bounds from which you can get that you need to have at least 1 over root n probability beyond half. So you need to, if you have only n samples available, then you can distinguish between a coin which has bias half and a bias half plus minus 1 over root n. And that 1 over root n is where the sigma sub root n is coming. So if you need 1 over root n mass, then you need to go at least a distance which is sigma root n. Okay, so that's the rough idea of sample median. And so sample mean is one approach, sample median is another approach. So what these approaches are doing, they are essentially what is called M estimators. So you might recall that the mean or the sample mean is something that minimizes the squared L2 loss. And the median is something that minimizes the absolute value loss. And the problem with these loss functions uh, is that these loss functions go to infinity as x goes to infinity. So of course the rate of growth for the absolute value is much slower than the rate of growth for x square, and that's the reason why median is more robust. So when you get an outlier, when you get something that is very far away, so then x square is much bigger than x, so the loss function is very largely affected when you have outliers. But that does give us an idea that why are we looking at loss functions that are increasing. If you want to get the tail probability kind of out of the picture, it's better to look at a loss function which is as is shown. So after a certain point, the tail just doesn't affect your loss function at all. And that particular loss function gives rise to what is called the mode estimator. So mode, recall, is the peak of a probability density. Um, so this kind of an estimator is called the mode estimator. So I'll describe what exactly the R modal estimator is. So again, recall that we are just going through the list of commonly used estimators. So we did mean, we did sorry, we did yeah, we did mean, we did median, and now we're discussing the modal estimator. So the modal estimator is quite easy to describe. It's just trying to figure out what is the interval which contains the maximum number of points. So let's say you decide some radius r. So that's basically the length of the interval in the beginning. You try to find out the point theta such that the interval theta minus r to theta plus r contains a maximum number of points. So of course, as you change theta, the number of points in the interval changes, and at some point it's maximized, then you output that point. Okay, and so this modal estimator has been studied in classical statistics. It's related to this Chernoff modal estimator that was discovered, I think, in the 60s, and we do know some things about it. So recall that the mean and the median have an error that is like 1 over root n. So because the variance of x1 plus x2 plus xn over n is sigma over root n, a sigma square over n. So the error is sigma over root n. But in the modal estimator, the error is not 1 over root n, it's 1 over cube root n. So it's actually a worse error than the mean. And the analysis of calculating the error relies on the curvature of the density at the mean. So that gives us an idea that maybe the thing to look at is this average distribution p1 plus p2 plus pn over n, and look at the curvature of this p bar and then try to figure out whether the modal estimator will work better than the mean or the median. Okay, so the intuition that we have is that when you're in a clean data setting, when there are no such outliers where sigmas are kind of all the sigmas are well behaved, then mean and median work well. But when you're in a situation where the sigmas can be really completely extremely bad, then in that situation you want to use something like the modal estimator. Even though for i.i.d data it performs worse, when you have such outlier samples, modal estimator performs better. All right, so as I said, we are going to try and look at this p bar, which is the average of all the probability distributions that we have. And one example of this is that you have log n distributions that are good. So as I said, you have log n good reviewers whose variance is, let's say, a constant 1, and everyone else has a variance which is increasing. So n to the 2 alpha. So the millionth reviewer has a reviewer of million to the 2 alpha. So you can plot this distribution p bar in this case and see that as n goes to infinity, it becomes extremely flat. And that's understandable because the variance n to the 2 alpha is increasing and the bad points are far more numerous than the good points. So the density basically ends up being very, very flat. But even if the density is flat, you can observe that there is that small peak near zero. So zero is the true mean here. There is that small peak. So there is a curvature around the true density. So that gives us some indication that even if it is becoming flat, you should still be able to detect where the mean is, because the empirical density should still have more points near me. And you can formalize this by using some concentration inequalities. These are very similar to VC dimension, like bounds. So you look, these are uniform concentration bounds. So you look at all these intervals whose length is at most r, and you can show that there is this. Okay, so let me go through the notation. So the expectation with respect to p bar is the expected number of points that you expect to see in an interval according to the p bar density, whereas the expectation according to p bar n is the empirical fraction. So how many points actually landed up in that interval. Now, of course, if you have infinite number of points, and then the fraction of points that land up in an interval is going to be very close to the expected number of points. So what this theorem in the last bullet point is trying to say is that in fact you have this uniform concentration result. So no matter where that interval is placed, you are assured that the number of points, the fraction of points that lie in the interval does not deviate from the expected number of points by more than, let's say, zero point 0.1 times the expectation in the best possible interval. So the interval that is sitting at mu. And so this is a uniform concentration bound. It says that over all intervals, this probability of error, sort of bad event, goes to zero. And you can use this concentration bound to get an error bound on the distance between mu hat and. So using the concentration bounds, what you can conclude is that uh, if you look at the interval around mu hat and the interval around the true mu, the difference in the probabilities there is very small. So you need to now convert the distance in probabilities to distance between the mu's themselves. Okay, so you can see that when you have a distribution with very high curvature, then as you go away from the mean, so mean is in this case zero on the left hand side, as you go away from the mean, the probability in an interval that very rapidly goes down. So if the difference in probability is small, then that means that the difference in the mu and mu hat is also going to be small. But you can also have distributions which are extremely flat, in which case your difference in probabilities can be small, but the difference in the mu and mu hat can actually be very large. Um, so what ends up happening is that you can calculate what the worst case error is, and the error depends on the curvature of this p bar. In particular, you get an error that depends that in the worst case behaves like n times sigma log n. So recall that sigma sub log n is the log nth smallest variance. So if you're looking at the modal estimator, your variance behaves like n times sigma log n. Right. So far we've seen three. We've seen the mean, the median, and the modal. There are two other estimators that I'll very briefly discuss. One is the k shortest gap estimator, which is also called the shorth estimator. And this is a very clever estimator. So what it does is you have these n points that are on the real line. You try to find the smallest interval that contains at least k points. So k in this, for now, just think of k as being, let's say, n by 2 or something. So it's the smallest interval that contains half the points, and then you output, let's say, the midpoint of that interval. So this k shortest gap estimator turns out to be, again, it has a very similar performance to the modal estimator. In particular, it has a convergence rate for i.i.d data of 1 over cube root n. So again, it is worse than mean and median for i.i.d data. But when you have outliers, it's much better. So for instance, it only depends on the log n smallest variances, whereas mean requires all of them to be good, and median requires square root n to be good. So k shortest gap and modal only require log n good variances. And the performance of k shortest gap is very similar to performance of the modal, with k and that r suitably chosen. Right, and the last one that I'll discuss is the k median. This was proposed by this was proposed by the authors in a paper in 2014, Cherry Chetty et al. And what this estimator does is, instead of looking at the interval with the k points that are closest to each other, you try to find the k points that are centermost. So the median is basically the centermost single point, but a k median is centermost k point. So if you want a 3 median, you take the centermost point and the point to its left and point to its right. And this is kind of a more global estimator. You have to look at all the points to figure out which one is the middle point, which one is the left, and which one is the right. And if you look at the square root nth middle point, so if k is at least square root n, then you can show using the same intuition as the coin toss that the true mean lies in that square root nth interval with very high probability. Okay, so what the k median does is it gives you an interval such that the mean is the true mean is very almost certain to lie in that interval, and it also tells you that the size of this interval is roughly the same order as that of the median. So like sigma of square root n. So one trick that we can use is that perhaps what if you do the modal interval first, modal estimator first, and then project it onto this interval that is given by the mean. And the intuition for why one might do this is that there are certain regimes in which the median works well. There are certain regimes in which the modal or the shorth estimator work well. Um, and projecting the modal interval or the shorth estimator onto the median can only make it better, because you are assured that the true mean lies in that interval. So if the modal estimator already lies inside the k median, then nothing happens to it. It remains what it is. If it's outside the interval, then it goes inside the interval, and then it only becomes better. Like the distance from the true mean only goes down. So that's the idea of the hybrid estimator that we propose in this work. That you have several well-known estimators, but they all seem to work in different ranges of variances. So perhaps we can combine these to get a new estimator that does better than all of them in all regimes. And that's basically what's happening in this table here. So the table here is showing four estimators: the mean, median, mode, and hybrid. So for the mode, you can also think of mode and shorth as being interchangeable. Um, so if you look at the first row, it tells you what happens when you have i.i.d data, that the mean and median perform much better than mode, but the hybrid performs just as well as the hybrid performs just as well as the mean and median, because your hybrid is as good as the median. So it goes on to it's as well as the median. The second row is telling us what the breakdown point is. So roughly the breakdown point just means that how many bad points do you need to completely mess up the estimator. So for the mean, even a single bad point will mess up the estimator. For the median, you need n minus square root n bad points. And for the mode, you need n minus log n. So mode is the most robust in this sense. And the hybrid is as good as the mode. So the hybrid works by calculating the mode and projecting it on the median. So hybrid turns out to be as robust as the mode. Um, the third row is telling us what is the worst case error. So the worst case error in mean is determined by the largest variance. So sigma sub n is the variance of the maximum possible variance. In median, it's determined by the square root nth largest variance, and in mode, it's determined by the log nth square root nth smallest variance. I'm sorry, and in the mode, it's determined by the log nth smallest variance. And interestingly, in the hybrid, you get something that is much better than all of them. So you get the log nth variance, but instead of n times sigma log n that happens in mode, you get square root n times sigma log n. And the intuition here is So we are doing this hybrid. So the intuition here is just that when you do the median, you're only looking at square root n points that are sitting in the middle. So what you're roughly doing is you're basically getting rid of all the outliers. So everything that is outside of those square root n points are now irrelevant. So in some sense, your n has gone down from n to square root n. That's why your error, which used to be n times sigma log n, went down to square root n times sigma log n. Okay, so that's roughly the intuition, but the analysis doesn't exactly go through if you interpret it like that, because once you restrict yourselves to the square root n points in the middle, and get rid of the outliers, then the remaining square root n points that are in the middle are no longer independent. So uh, one of our working assumptions is that the points are independent but not identical. But when you do this filtering step, basically the points stop being independent, and that causes some issues. So that's why the analysis is a bit different, but that's roughly the intuition for why doing the median and mode together can get you a much better error. Okay, and the last two rows are telling you have a specific example of the alpha mixture distributions. The alpha mixture distribution is explained at the bottom of the slide. So again, the thing to notice here is that the hybrid estimator does as well as the best of these. Um, and again, it's kind of pointing out that there are regimes where the mean and median do well, and there are regimes where the mode does well. So when alpha is less than 1, so that means that the bad points are not that bad. Mean and median do well, but if the bad points are really bad, like the variances of the bad points are really high, then mean and median perform really badly, but mode does well. And the hybrid model somehow figures out what situation you're in, and adapts the level of heterogeneity in the data. Okay, right. So we have some optimality bounds as well, that you might also ask, sure, the hybrid is achieving these error bounds, but is that the best? Is there something out there that can do even better? So at least we have several regimes of interest where you can show that you cannot do better than what the hybrid is already doing. And one such regime is this alpha mixture with alpha less than 1, where we can show that there is a lower bound of n to the alpha minus 0.5. You cannot beat that, and the hybrid estimator achieves that. Um, one interesting thing that happens for this alpha mixture distribution is that um, if you look at the previous slide, when alpha is less than 1, if you look at the error of the hybrid estimator, for instance, there is a phase transition. So the moment alpha becomes less than 1 to greater than 1, the error goes from something that is increasing, so is something that is not consistent, to something that is bounded. So suddenly n to the alpha minus 0.5 goes down to a constant. So there's in fact like a phase transition in the difficulty of the problem. So intuitively what is happening is that if the variances of the bad points are so bad, that really large, then it's very easy to spot which the good points are and which the bad points are, because the good points are all clustered together, the bad points are really far away. That makes the problem actually easier to solve, right? So you can also so far the entire discussion was for one-dimensional distributions, but pretty much the entire theory that I discussed goes through even when you have higher dimensional distributions. You just need to continue to have the symmetry assumption. So for the one dimension, maybe I didn't mention it, but we always have a unimodality and symmetry assumption, that the distributions are centered at the true mean and they are symmetric around that. And you need to have a similar assumption in high dimensions, that the distributions are centered at the true mean and they are spherically symmetric. And you don't really need strict symmetry. What we really need is that all mean, mode, and median are all close to each other. All right, so for multivariate data, the dimension also sort of so what techniques could one use to solve the multivariate problem? So it turns out that if the dimension is large enough, if that dimension is greater than log n, then you can just estimate the sigma. So recall that we are in the situation where sigmas are unknown. But if D is large enough, then you can just estimate the sigmas and then use the maximum likelihood estimator. So that makes the problem much easier. So the more interesting case is when the dimension is actually low. So dimension is O of log n. And can we do better than a simple coordinate wise estimator? So coordinate wise means that we just think of each dimension as being separate problem, and in each dimension our hybrid estimator is giving us square root and sigma log n error. You do it in each dimension, you get that square root d factor sitting outside. And the question is, can you do better than just a simple coordinate wise error? Um, and the answer is yes, and the intuition is as follows, that uh, basically when you have good reviewers, if you know that a particular crowdsourcing reviewer is a good reviewer, then you can trust their judgment for all items. So now, once you have identified a good reviewer, you know that all their ratings are good, not just for item I, but for every single item. So roughly, another way to think of it is, there's only one way to be a good reviewer, and that means you are estimating the muse correctly. But there are many ways to be a bad reviewer. A bad reviewer doesn't have bad reviewer can give ratings that are far away from the actual view. And the bad reviewers don't necessarily have to agree with each other, but good reviewers always have to agree with each other. And that helps you that helps you get a better error guarantee. Um, the kind of the estimator that we'll end up using is very similar to what we did in one dimension. This is the modal interval estimator, but now with spherical balls. So you try to find out what is the ball of radius r that contains a maximum number of points and output the center of that ball. So like in the 1D case, we have these concentration bounds that the probability of the p bar measured at mu hat is close to the probability measured at mu, but that needs to get converted into a bound for mu hat minus mu. And I won't go into too much detail, but roughly you have these several things in high dimension actually help you. And these once you combine what you get from the 3 bullet points that I won't get into, what you get is that the worst case error of this modal interval estimator is square root d n to the 1 by d sigma log n. So again, the good thing is it depends only on the log n smallest variances. And when d is equal to 1, it exactly agrees with the bound that we got in one dimension. But recall that in one dimension, we could go from n times sigma log n to square root n times sigma log n by using the hybrid estimator. So the question is, can we go from n to the 1 by d to something better by using a hybrid estimator? And the difficulty, or at least the first challenge there is, in one dimension, it's very easy to define this k median. So that's the k points that lie in the middle. But in high dimensions, there is what do we mean when we say k points that lie in the middle? Because there is no strict ordering between all the points. Um, so it turns out, actually, I will skip the computational efficiency slide. So it turns out that coordinate-wise median works. So what you do is, in every coordinate, you find out the square root n points that lie in the middle, and that gives you an interval for each coordinate. And then you take the cuboid, which is like the which cuboid that is formed by each of these coordinate-wise medians. And it turns out that this cuboid can now serve as your substitute for the square root n median that worked in one dimension. And to make sure this works out, you need to somehow relate the one dimensional marginals to the joint density. And once you have this cuboid, then projecting things on a cuboid is really easy. It's just order n, and this new hybrid estimator does exactly what we want to do. That the error which used to be n to the 1 by d sigma log n now goes to n to the 1 by 2d sigma log n. So essentially, this completes the story for completely translates what we knew in one dimensions to higher dimensions. Right. And what are some other generalizations that one might look at? Well, once a natural setting in statistics, once you have done mean estimation is regression. So let's say you have a statistical model where you're getting these xi, yi samples, and you know that yi is xi transpose beta star, where beta star is something that is unknown, plus epsilon I, where epsilon I now has Gaussian distribution with unknown variances. So when epsilon I are just Gaussians with known identical variances, then this is like the standard regression setting. But we are tweaking it by saying that epsilon I now have different variances, and those variances are unknown. Now, the ideas that we used in modal estimator suggest that perhaps the thing to do is to try to find that beta hat, so that the yi minus xi transpose beta, which is called the residuals, so you get the maximum number of residuals in the interval around a radius of r for that value of beta hat. And what we could show is that if you do come up with this estimator, so again, what the value of r is depends on the sigmas, and at least for the regression problem, we don't yet know how to figure out this r using data. We do know it for the mean problem, but for regression, that's kind of an unsolved problem so far. But if somehow you are able to estimate r, then your estimate of beta hat and beta are about order n sigma log n things. And there are quite a lot of interesting questions remaining here. So one thing is, um, how do we find this? Right now our theory only works for Gaussian noise. We're not really sure how to extend it to general spherically symmetric noise, and we are also not entirely sure if the computational complexity of finding beta hat can be reduced. So right now we have like some order n to the d algorithm that it's still polynomial, but it's in high dimensions it can be quite bad. So there are a lot of interesting questions in the regression setting, and some open problems. So we were able to show that this hybrid estimator is good in several regimes of interest. So good in the sense it's min max optimal, but we don't really know in complete generality whether for any given sigmas is it always the best thing to do, or is there something that is better than the hybrid estimator. Again, the questions for regression are quite open, that we don't know computational and statistical efficiencies of regression. Um, right now, pretty much all the theory that we have is limited to largely symmetric and unimodal distributions. So if you have multimodal distributions, nothing that we have done so far works for multimodal distributions. And lastly, like this line of work just gives an idea that if you take your favorite statistical model, like we did for linear regression, and add this twist to it, that the noises that are added to it are no longer i.i.d, but you're going beyond i.i.d and making them independent possibly, but not identically distributed, with the added twist that you don't even know what the sigmas are and try to figure out what's the best you can do. So that pretty much brings me to the end of the presentation. The reference for this is the paper Estimating Location Parameters in Sample Heterogeneous Distributions. This is work done largely by my student, Ankit Pensia. He is currently a fifth year graduate student in the computer science department in UW-Madison. And the paper was recently published at the Information and Inference journal this year. A conference version of it was also presented at ISIT in 2018. So that's the end of my presentation. Please feel free to ask me any questions.
Thank you, Varun. Thank you very much for this very interesting talk. Is there any questions from the audience?
Yeah, thanks to all the audience members for showing up. I imagine like they're all over the world, and some of them are waking up really early, others are staying up late. So
Yeah,
thank you for showing up.
no worries. I'm not very familiar with the classical statistical inference problems. But so the orders you obtain are sort of the first order, since you use some concentration inequalities. So
Right.
so my question is it possible to obtain certain higher order terms in your estimate, or is that important at all?
So roughly like the way the bounds are obtained, they are actually high probability bounds that with probability 1 minus e to the minus c times n. So like with very high probability, the estimate lies within a certain bound. And typically like as long as you get 1 minus as long as you get like 1 minus e to the minus n kind of bounds,
It's very
uh,
high.
yeah, that's good enough. Like you don't really people don't really care about optimizing how fast it is actually what that constant c is, or even in the bounds, like there are all sorts of constants floating around that we don't really care about. Like it's just the order that matters.
Uh,
um
uh,
yeah.
so the constant you meant is the like prefactor of the
uh,
exponential.
no, I guess the constant is so these are like universal constants that you decide in the beginning,
Yes.
and the constants tell you that. So when I said it's the let's say sigma log n, so it's the log n at smallest variance that controls error. It could be c log n. I mean, it's like 10 log n or something. So those constants
Okay.
are sort of floating, and we don't really determine them exactly, but we know that it's going to be some order log n.
I see. I see.
Yeah.
Okay. I don't see any questions from the Slack channel. So if the audience has any question, please turn on your microphone. Okay, I think there's no more questions, and it's very late time for speaker. So I think we can end this talk here. And let me thank Varun again for this very interesting talk. Thank you.
Yeah. Thanks a lot for having me. Yeah.